Welcome to our explainer. Today we're diving into a really fascinating theory, one that looks for the hidden poetry in, of all places, mathematics.
You know, we usually think of numbers as just cold, hard facts. 2 is 2, 10 is 10. That's it. But what if they were more than that? What if every single number had its own personality, its own character, a story just waiting for us to uncover it?
Well, that's the big idea behind a framework called Teori Coherent Perhubungan Munasabah, or MRCT for short. Think of it as a special lens for looking at numbers, not as these isolated values, but as part of a huge, interconnected web of meaning. It's all about finding a hidden harmony.
So here's what we're going to cover. First, we'll get into the philosophy behind MRCT. Then we'll break down its 4 core pillars. We're going to put a number, 15876, to the test. We'll also explore why any of this matters outside of pure math. And finally, we'll see the beautiful connections this theory claims to reveal. All right, let's get into it.
So what is MRCT really about? At its heart, it's a challenge to how we see things. It's asking us to stop looking at numbers as just random points on a line, and instead to start seeing them as, say, stars in a hidden constellation, all part of some bigger logical system. The whole theory is actually grounded in the Malay concept of munasabah. Now, this word doesn't just mean logical. It has a much deeper sense of appropriateness, of reason, and harmony. And MRCT suggests that the entire world of numbers has this very same quality, an inherent reasonable harmony, but only if you know how to look for it.
Okay, so how do we find this harmony? Well, MRCT gives us a toolkit. It's made up of 4 tests or pillars that help us measure a number's coherence. You can think of them as 4 different ways to really understand a number's character.
First up, we have our first test for a number. It's called the pillar of absolute simplicity, or rep digit.
This one's the easiest one to spot for sure. A rep digit is just any number that's made by repeating a single digit. You know, like 111 or 7777, it represents the most basic, most intuitive kind of pattern you can imagine.
Now, on the complete opposite end of the spectrum, the second pillar looks for a very specific kind of elegant complexity, and this is the sphenic test.
A sphenic number is the product of 3 different prime numbers. So take 30, for example. That's 2 times 3 times 5. This unique structure actually makes them really hard to factor, which is a super important property used in cryptography to keep all our data secure. Our third pillar is a bit more introspective. It's called Harshad, and it's all about a number's relationship with its own digits. So here's the key thing. A Harshad number can be perfectly divided by the sum of its own digits. The classic example is 18. You add 1 plus 8, you get 9. And since 18 is divisible by 9, it creates this really neat self-contained loop of internal harmony. Kind of cool, right?
And that brings us to our fourth and final pillar, which tries to find a number's true essence. It's called the digital root. This is basically a process for boiling any number down to one single essential digit. All you do is add up all the digits. If that sum is still more than 1 digit, you just do it again. So for our case study number, 15,876, the digits add up to 27. We do it again. 2 plus 7 gives us a final digital root of 9.
So there you have it, the 4 pillars. Rep digit for pure simplicity, sphenic for that structured complexity, Harshad for internal harmony, and digital root for its essential core. Now let's get to our case study and see how this all works in the real world. All right, we are going to put the number 15,876 through the MRCT gauntlet. I want you to think of it like a character on a quest, being tested by each of these 4 pillars to see if it has that munasabah or coherence.
Let's check out the scorecard. As you can see, for R1 rep digit and R2 sphenic, the result is gagag, which means fail. I mean, that's pretty obvious, right? Its digits aren't repetitive and its prime factors aren't structured the right way. But here's where it gets interesting. It passes the other 2 tests. It is a Harshad number, and like we just calculated, it has a digital root of 9.
So it passes 2 out of the 4 tests. And according to this theory, any number that satisfies at least 2 pillars is considered coherent. It's found the balance. It's not perfectly simple, and it's not elegantly complex, but it has its own special kind of internal harmony.
And this chart just illustrates its personality perfectly. If you look at the plot, you can see our number, 15,876, sitting right there in the top right quadrant. This shows it has a balance of high complexity from its factors and simple harmony from being a Harshad number. It's really carved out its own unique little spot in the numerical landscape.
Okay, this is a neat philosophical exercise, but does it have any use in the real world? Well, surprisingly, the answer is yes. This isn't just about finding patterns for the fun of it.
The very properties that MRCT highlights are actually super important in some surprising fields. Harshad numbers, for instance, can be used in checksum algorithms, to make sure your data hasn't been corrupted when it's sent. And the process of finding a digital root, that's actually a basic form of what's called dimension reduction, a technique used in AI to simplify huge datasets and find hidden patterns. The theory even stretches to physics and psychology, helping us understand everything from quantum states to why our brains are so drawn to harmony.
But the true beauty of this theory, at least according to its proponents, isn't just about classifying numbers. No, it's about revealing the unexpected, sometimes profound relationships between them.
Just take a look at this path of discovery. This is not your typical mathematical proof. The theory uses these intuitive steps, like taking the sum of the digits, or reversing them, or linking them with related primes, to build this chain of connections. And incredibly, this path leads from our humble 15,876 all the way to 1729, that legendary taxicab number from mathematical folklore. It suggests that numbers aren't just islands. They're all part of one big interconnected story.
So what MRCT does is it invites us to look at the world of numbers not as some rigid set of rules, but as a language full of stories and personalities and hidden connections. And it leaves us with one final thought. If a seemingly random number like 15,876 can have such a rich inner life, what narrative might be hiding in your own favorite number, your address, or even your birthday? What story is it just waiting to tell?